Hey, so today we're going to be doing a question from the 2019 AP Chemistry free response. You can get it pretty easily, just, Google it, it's online. Um, and what you should do is read through the question and try to complete it before you work through it with me and watch this video. I'm going to do number 4 first because there was a request for a gas law problem. So number 4 says, a student is doing experiments with carbon dioxide. Originally, a sample of the gas is in a rigid container at 299 Kelvin and 0.70 atmospheres. The student increases the temperature of the carbon dioxide in the container to 425 Kelvin. Describe the effect of raising the temperature on the motion of the CO2 molecules. Well, when you look at the formula for kinetic energy, and if we remember, temperature is just a measure of the average kinetic energy of a sample. And when you raise the temperature, you raise that average kinetic energy. And it would, it's pretty much common sense that, if something has a higher temperature, it has more kinetic energy, more energy of motion. And so when you look at the other side of that equation, the 1/2 mv squared, the mass of the carbon dioxide isn't going to change. So the only thing that can change is the velocity. So they're going to be moving a lot faster. And if they were in, just a flexible environment or an open area, they would also expand. But that's not an option since they're in a rigid container. So what they would do is they would have more and more violent collisions in addition to the increased velocity. So describe the effect of raising the temperature on the motion. The CO2 molecules would be going faster. They would have a higher velocity. And in addition, since they are moving around faster, they would have more and more violent collisions. Calculate the pressure of the CO2 in the container at 425 Kelvin. So, we're always expecting them to bust out the ideal gas equation, but we don't have any indication of the mass or the moles or anything. So I'm going to do combined gas law, P1 V1 T2 equals P2 V2 T1. And then I'm going to get rid of the volume because the volume's not going to change because it's a rigid container. And so that leaves me with P1 T2 equals P2 T1, which is Gay-Lussac's law. And so my first pressure is 0.70 atmospheres. And then I'm going to match that with the T2, which is 425 K. And remember, we always want Kelvin here because we don't want negative numbers. And Kelvin doesn't have any negatives. And then I'm going to put the original temperature, 299 K, right here. And let me show you how that sets up here. So, see, that's not bad. And remember, there are really only 2 gas equations you need, the ideal and the combined. And then you can derive anything you need out of the combined, Boyle's law, Charles' law, or Gay-Lussac's. And so now I just have to move that temperature over there. And remember, the temperatures are on the opposite side because of the relationship of temperature and volume, okay? So don't, it's real easy to go P1, V1, T1, but it's not. It's P1, V1, T2, okay? So I'm just going to go 0.7 times 425 divided by 299. And so the pressure does go up. And that's what we would expect. It goes up from 0.70 to, I mean, it's pretty much 1 atmosphere at that point. Okay, so that's how we solve the B answer. In terms of kinetic molecular theory, briefly explain why the pressure of the CO2 in the container changes as it is heated to 425 Kelvin. The pressure is going to be changing because it has more and more violent collisions, and it's going to be colliding with the side of the container, and those molecules are going to be colliding with each other, and the increased frequency of those collisions are going to cause a raise in the pressure. And, you know, pressure and temperature, you know, when you raise the temperature and it can't expand, it's, you know, definitely going to pressurize that container. So that's kind of the answer. It's the answer to C. And then D, the student measures the actual pressure of the CO2 in the container at 425 K and observes that it is less than the it's less than the pressure predicted by the ideal gas law. Explain this observation. Well, you know, the thing is, when we use the ideal gas law, even though it's interesting they invoked the ideal gas law when you weren't using the ideal gas law in the problem, but beside the point, I'm also getting some emails here. What happens is whenever two gas molecules collide, the ideal gas law posits that it's a perfectly elastic collision, but in reality, there are no perfectly elastic collisions. And whenever they collide, and we talked about this in class, they stick together just for a second, and not even a second, like a microsecond. And that little instant of sticking together makes it an elastic collision, and therefore not, and it just shaves a little bit off of that expected pressure. So that's 4D, and that took 7 minutes and 45 seconds.